Hello and welcome back for some more reinforced concrete design. Today we'll be discussing subframe analysis. Reinforced concrete structures behave as rigid frames. Therefore, they can be analysed as space frames or a series of plane frames. Slabs are analysed as continuous members supported by beams or structural walls. Depending on the ratio between the side lengths, slabs can be considered as working in one way or two ways. Columns and main beams are analysed as a series of rigid plane frames. Axial forces in columns can be calculated, assuming that the beams and slabs are simply supported. Frames can be braced or unbraced. The braced frames support vertical loads only, while the lateral loads are resisted by shear walls, lift shafts, or stairwells. The unbraced frames support vertical and lateral loads, where the lateral loads can also cause bending, shearing, and axial loads in beams and columns. Braced frames can be analysed for vertical loads either as complete frames or a series of substitute frames, in short, subframes. The substitute frames vary in complexity and can include either a complete floor beam with connecting columns or a single span beam combined with connecting columns and beams, or a single junction with connecting beams and columns. Here you can see examples of the division of a multi-story frame into substitute frames of different complexity. Let's discuss these subframes in a bit more detail. The most complex subframe consists of a complete floor beam with connecting columns. The analysis of this subframe gives moments and shear forces in beams and columns for the floor level. A simpler subframe consisting of a single span beam combined with connecting columns and beams is shown here. The analysis of this subframe gives moments and shear forces in the central beam and columns. The simplest subframes consist of a single junction with connecting beams and columns where the junction can be external and internal. These subframes can only be used for calculation of moments in the columns when beams are analysed as continuous over simple supports. Subframe analysis is a quick and easy way to get design moments in indeterminate braced frames. As we discussed, the subframes consist of beams at one level and columns above and below. The ends of the columns away from the beam are assumed to be fixed, unless pinned is more appropriate in the situation. The fixed end assumption overestimates member stiffnesses. Therefore, the stiffnesses of connecting beams are halved to allow for the flexibility resulting from continuity. Overlapping frames can be used if necessary. Beams are analysed as separate fixed-ended entities with alternate spans loaded by the maximum and minimum loads, since such loading arrangements give the worst cases. The design moment for the column is obtained using stiffness-based formulas, where the coefficients are obtained using the slope deflection method. The relative stiffness of members is calculated based on gross concrete sections, and the geometry of flanged beams is calculated using the effective width. The effective width of the flanged beams depends on the supporting conditions and flange shape, as shown in this table. Various load cases producing maximum moments as well as shear and axial forces should be considered. Every span is loaded by either the maximum uniformly distributed load, equal 1.35 times the permanent load plus 1.5 times the variable load, or the minimum uniformly distributed load of 1.35 times the permanent load. Cantilever spans may also be loaded by the permanent load only. Critical load cases for columns should also include maximum moment and minimum possible axial force. This case leads to tension failure due to bending. Let's consider two simple subframes with a single external and internal junction. The design moment for the bottom end of the upper column can be found as the moment applied at the junction by the beams times the ratio of the upper column stiffness to the total stiffness of the junction. As you can see, the left subframe connects one beam and two columns at the junction, and therefore the total stiffness of its junction consists of three components. The right subframe connects two beams and two columns at the junction, and therefore the total stiffness of its junction consists of four components. Accordingly, the design moment for the top end of the lower column can be calculated as the moment applied at the junction by the beams times the ratio of the lower column stiffness to the total stiffness of the junction. And the stiffnesses of beams and columns can be found using similar formulas, with the difference that the stiffnesses of beams are halved to allow for the flexibility resulting from continuity. Let's consider an example with a simple subframe consisting of an internal junction connecting two beams and two columns. Both beams are 6 meters long and are loaded by uniformly distributed loads of 30 kN per meters and 60 kN per meters. The beams are twice as stiff as the columns, and we need to find the design moment for the top of the lower column. The solution starts with the calculation of end span moments in the beams with both ends fixed. The end span moment in the left beam loaded by 30 kN per meters equals 90 kN meters. The end span moment in the right beam loaded by the 60 kN per meters equals 180 kN meters. And the design moment for the top end of the lower column is calculated as the difference between the end span moments in the beams times the ratio of the lower column stiffness to the total stiffness of the junction. This gives us 15 kN meters. I hope you found that useful, and I hope to see you again for some more reinforced concrete design.